Hello students, welcome to the e-learning platform presented by Mechanical Engineering Department of Dr. Bapuji Saloke Institute of Engineering and Technology, Kolhapur. The learning objectives for the today's session will be number 1, study of air standard cycle. Air standard cycle, mostly we use air fuel mixture as our working fuel in IC engines. For this purpose, the air is considered as a major part and based on which cycles are designed, which we will be studying in the further coming sessions. In this today's session, we will be learning about the air standard cycle, that is Carnot cycle. Second, application of air standard cycle. Application of air standard cycle will be studied in this today's session. Let us start with air standard cycle. In most of the power developing systems such as petrol engine, diesel engine and gas turbine, the common working fluid used is air. These devices either take a mixture of fuel and air as in petrol engine or use fuel separately and mix them in combustion chamber as in diesel engine. The mass of the fuel used compared with the mass of the air is rather small. Therefore, the properties of mixture can be approximated to the properties of the air. Exact conditions existing within the actual cylinders are very difficult to determine, but by making simple certain assumptions, it is possible to approximate these conditions more or less correctly. The approximate engine cycle analyzed are known as theoretical cycles. The simplest theoretical cycle is called as air cycle approximation. The air cycle approximation used for calculating the conditions in internal combustion engine is called as air standard cycle. In short, the conditions that are used to calculate the air cycle approximation in an internal combustion engine is called as air standard cycle. In order to compare the thermal efficiency of an actual running engine performance with the theoretical efficiency of an ideal cycle using air as a working fluid, there are certain assumptions that are need to be understand. The following are the assumptions made for the air standard cycle. Number 1, a perfect gas is used. That is, the gas obeys the gas law. The gas used at the working medium obeys the gas law. Second, the transfer of heat does not affect the temperature of the source and the sink. The heat transfer takes place without affecting the other region, that is the source and the sink. Third, they are perfectly insulated. That is, the wall of piston, cylinder and cylinder head are perfectly insulated as in the case of engine, IC engine. Fourth, working fluid has a fixed mass. Working fluid has a fixed mass and does not undergo any chemical changes throughout the cycle. This states that the working fluid has a same mass throughout the working cycle. Fifth, they take place without internal friction. This is the most important assumption in the air standard cycle, that is, they take place without internal friction, as it is not possible in general IC engine to work without internal friction. And last, specific heat constants, that is Cp and Cv, are constants and do not vary with increase in temperature. In general, Cp and Cv are the constants that vary with respect to the temperature. But in case of air standard cycle, we have assumed that Cp and Cv are constant and they do not vary with increase in temperature. Because of many simplifying assumptions, it is clear that air cycle approximation does not closely represent the condition within the actual cylinder. Due to simplicity of air cycle calculation, it is often used to obtain approximate answer to the complex engine problems. First is Carnot cycle. Sadi Carnot in 1824 first proposed the concept of heat engine working on reversible cycle, that is no friction between the working, is called as Carnot cycle. According to the Carnot theorem, no cycle can be more efficient than a reversible cycle operating between the same temperature limits. Carnot cycle is useful to compare the efficiency of any cycle under consideration with the efficiency of any cycle operating between the same two temperatures. Carnot cycle is basically used to compare the efficiency with the actual working cycle. A Carnot cycle is hypothetical cycle consisting of different processes. Carnot cycle is actually a ideal cycle because heat addition and heat rejection is at constant temperature, uh, and it is a quasi-static process, and thus this process cannot be achieved in actual practice. There are two reversible isothermal process and two reversible adiabatic process which we are going to see. The figure below shows the PV and TS diagram of the Carnot cycle. There are four processes in Carnot cycle. Each process has a different meaning and works on different process. Number 1 is the process 1 2, and it is a reversible isothermal, that is at constant temperature. During this, air is expanded and heat addition is there at T1 temperature. Second is process 2 to 3. It is reversible adiabatic. Air expands at temperature T2 to T3. In this process, there is entropy, addition of entropy. So it is called as, also called as isentropic process. Third is process 3 to 4. Air is compressed reversible isothermally, that is without friction at constant temperature. At temperature T3, heat is rejected during this process. And last is process 4-1, that is reversible adiabatic. Air is compressed reversible adiabatically at temperature 4 T4 to T1. After understanding the processes properly, we move on towards the efficiency of Carnot cycle. The heat is added and rejected only two times, and due to this, heat supplied during the isothermal process 1-2 can be calculated using the formula Q1 is equal to RT1 log V2 upon V1. In this, R stands for the specific constant, Ln stands for specific constant, log T1 stands for the source temperature, and V2 and V1 stands for the volume at point 1 and 2. Q1 stands for heat supplied during isothermal process. Next, heat rejected during isothermal compression 3-4 can be given by Q2, and it is given by the formula, same formula, only the temperature changes, that is RT3 log V4 upon V3 as shown in the video. Okay, heat rejected and heat supplied during the isothermal processes is only considered as during adiabatic expansion 2-3 and adiabatic compression 4-1. The heat transfer to the system and from the system is 0. The total net work done is given by W is equal to Q1 minus Q2. Substituting the value of Q1 and Q2 in W, and we know R is nothing but the compression ratio given by V2 upon V1 and V4 upon V3. In above equation, we get W is equal to R log into small r, that is compression ratio, into T1 minus T3. This is the net work done. The basic efficiency of any cycle is calculated by output upon input into 100. In Carnot cycle, the thermal efficiency is calculated by the formula efficiency is equal to work done upon heat supplied. In the previous session, in the previous part of the video, we saw how to calculate the work done for the Carnot cycle and heat supplied for the Carnot cycle. Using the above same values, we can calculate the efficiency of an Carnot cycle as Q1 minus Q3, that is work done, upon Q1, that is heat supplied. Substituting the values of Q1, Q3 in the efficiency equation, we get efficiency is equal to R log of R, that is compression ratio, into T1, that is temperature of source, minus T3, that is temperature of sink, upon R T1 log of R, that is compression ratio. Removing the similar values, that is R log and small r, that is compression ratio, we get efficiency is equal to T1 minus T3 upon T1. This can also be written as efficiency is equal to 1 minus T3 upon T1. This is the efficiency of Carnot cycle. Carnot cycle or Carnot heat engine is an ideal engine and is not possible in practice, and it has a certain reasons. The formula for efficiency, calculating the efficiency of Carnot cycle, is 1 minus T1 upon T3 upon T1. In this, if the T3 decreases, the efficiency increases. To attain 100% efficiency, the T3 temperature should be 0, but in actual condition it is not possible. For this reason, Carnot heat engine or Carnot heat cycle is called as an ideal heat engine and not possible in practice due to the following reason or due to the following limitations. Number 1, the Carnot cycle is hypothetical. Alternative reversible adiabatic and reversible isothermal processes are not possible. That is, heat addition and heat rejection at constant temperature is not possible. Second, the thermal efficiency of Carnot cycle depends upon absolute temperature of heat source T1 and heat sink T1 and T3. Third, practically it is not possible to neglect friction between the piston and cylinder. We know that there is a friction between the two moving parts. So practically in actual working condition, we cannot neglect the friction between the piston and cylinder. Fourth, it is impossible to construct the cylinder walls which are perfect insulator. There are the in Carnot cycle, the heat addition or rejection takes place at isothermally, that is at constant temperature. It is not possible because it is impossible to construct the cylinder walls which are having perfect insulation, that is no heat transfer takes place. Other than this, there are also some limitations, such as isothermal process requires a very small or very slow speed of operation, and it is very difficult to obtain in this mechanism. This all processes are reversible, that is, reversible means it is not having internal friction, which is not possible in our actual cycle. Due to this following limitations, Carnot cycle is basically used for calculating or comparing the efficiency of other cycles. In today's session, we studied about the air standard cycle, its assumption, Carnot cycles if thermal efficiency, work done, thermal efficiency, the derivation for thermal efficiency and work done has been asked in previous MSBT examination. Students are requested to take a note of the derivation of work done and thermal efficiency of Carnot problem, as there are numericals related to the Carnot cycle which we will be seeing in further sessions. Thank you. Hope you like